Today we're looking at section 4.7 for pre-calc, dealing with inverse trigonometric functions. Our objectives today will be to understand the restricted domains and ranges for the inverse trig functions and to evaluate some inverse trig functions. And then the next couple days we'll look at composing them and doing some applications of inverse trig functions. So a quick review. When we take the sine or cosine tangent, when we take a trig function, we are using an angle as our domain. We're taking the sine of an angle or the cosine of an angle or the tangent of an angle. What we get out for an answer is a ratio. Okay? So we take trig functions of angles to get ratios. When we get further into the notes and we start looking at our inverse trig functions, you'll see that that is reversed. All right, so we have a little experience with some inverse trig functions. We've done this type of question before. It said to find if the sine of theta is 5/7, solve for theta. Now, we did this with some of our known angles. This one isn't one of our known ones. So notice that we are solving for theta, which is supposed to be an element of the degrees from 0 to 360, that interval. So check that your calculator is in degree mode. Go ahead and pause the video if you need to fix that. And basically they're saying, let's just use one full rotation. All right, from 0 to 360, once around our unit circle, where do I have angles that have a sine of 5/7? So how we're going to do this is we're going to use an inverse function. Just like if we were solving, say, 2x equals 20, we would need the inverse of multiplying by 2 or multiplying by its multiplicative inverse, 1/2, to solve it. Okay? Well, the same idea here. We need to take the inverse of our trig function to undo that. So whatever we do to one side, we have to do to the other. All right, so with your calculator, I want you to type in inverse sine of 5/7. Now, to get inverse sine, you're going to have to use your second key and then the sine key. Okay? It should have a little sign with a little -1 exponent right above that key. So second sine of 5/7. And what we're getting out is basically our angle. So these two things here, our sine inverse with the sine, are going to cancel each other out. So with your calculator, you should be getting an angle of 45.585 degrees. Now, the one thing to be careful of is that's not the only answer. Okay? If we think about a unit circle, 45.585 degrees is splitting this in about half. All right? We have positive sine values in quadrant 2 as well. So we need to think about being over here in quadrant 2 with the same reference angle. All right, so our one answer is going from here to here, 45.585 degrees. Our second answer is going from 0 all the way to here. And to get that, we would have to take 180 minus our reference angle of 45.585. So 180 minus 45.585, and we should get 134.415 degrees. Okay, so we're getting two answers here. There's one, and there's one. So within one full rotation, there were two places where we had a positive sine of 5/7. All right, so notice that we had two solutions there, but if we're allowed to do many rotations around looking at all the different coterminal angles, we would have infinitely many solutions. All right, so it just depends on if they're limiting us to once around our unit circle or if we are allowed to have multiple rotations. All right, it says remember that for a function to have an inverse that is also a function, it must be 1-to-1. The 6 basic trig functions, being periodic, fail the horizontal line test rather spectacularly. However, since they are so important, we do look for a restricted domain where they will be one-to-one, thus allowing us to work with the inverse functions. So the domain that we are selecting has to fit these criteria. It has to show a one-to-one interval. That means it has to pass the horizontal line test. It has to take on all y values of the trig function, and it has to be convenient. So those are the three things we are going to look for. We're going to start with our inverse sine function. So let's go ahead and just graph a normal sine curve. Period for sine goes from 0 to 2 pi, splitting our interval into 4 increments. We have pi, pi over 2, 3 pi over 2. All right, each tick mark represents pi over 2. I'm going to have you go ahead and do the same thing on the negative side. All right, and let's go ahead and graph our sine curve. Sine starts at 0, goes to our high point of 1, back to 0, down to our low point of -1, and then back to 0. Okay, I want you to do the same thing on the negative side, getting a second period in here. All right, so we are looking at this graph, and you'll notice it's going to keep going in both directions, but it doesn't pass a horizontal line test. So what we have to do is we have to pick an interval where it does. So one option, I could start here and end here, and just looking at this part of my graph. That would take on all y values between -1 and +1, so I'm covering everything for y. It does pass a horizontal line test, so in that little section, it would be one-to-one. And in terms of how convenient it is, well, let's look at other options. I also could have used this one. Okay, still fits those same criteria. However, the best option would be to use this interval right here. Because it's centered on the origin, it's nice and close there. We don't have to shift over to say pi over 2 or negative pi over 2. It's just a little easier. Okay, so the interval that we're going to choose is going from negative pi over 2 to positive pi over 2. Let's include those endpoints. All right, and what we're going to do to get our inverse graph, we're going to start with the ordered pairs that we normally use here. So this point would be negative pi over 2, -1. We have the origin as one of our points, and we have the point pi over 2, 1. And when you do an inverse function, your x and y's just reverse themselves. So all of these ordered pairs are just going to flip-flop our x and y's. So we're going to have points -1, negative pi over 2, 0, 0, and +1, positive pi over 2. All right, so let's go ahead and plot those. Notice that when we switch our x and y's, that means instead of going from -1 to 1 on our y-axis, we're going to go from -1 to 1 on our x-axis. And instead of having the x-axis be our radian measures, we're going to have those be our y-axis. So we're up here at pi over 2 and down here at negative pi over 2. All right, plotting those points. First point, -1, negative pi over 2, puts us here. 0, 0, and +1 pi over 2 puts us there. And our graph is going to look like this. Now, we could plot other points. For example, we know the sine of pi over 6 is 1/2. So we could graph the ordered pair 1/2 pi over 6 and also get another point on our graph. But we're not going to take the time. I just want you to have kind of a visual of what those inverse functions look like. So in terms of our unit circle, if we are talking about an inverse sine function, we are saying that we can go from negative pi over 2 to positive pi over 2. We are only allowed to be in this section. So quadrants 1 and quadrants 4. Sine is positive in quadrant 1, and it's negative in quadrant 2. sorry, quadrant 4. Okay? So for our values here, domain are your x's. So we are going from -1 to 1. Range would be our y values, and it's called the principal value range instead of just a range because we are looking at just one little interval of our main sine curve. So our principal value range would be from -π/2 to +π/2. All right, that is summarized here in the chart at the top of the next page. It says the inverse sine function is the function f of x equals inverse sine of x with domain from -1 to 1 and range, that principal value range, of -π/2 to π/2. This means that x represents a ratio. Okay? X represents a sine ratio, and f of x represents an angle that's in either quadrants 1 or 4. Now, one thing to note, sometimes we'll say inverse sine. Sometimes you'll see that sine with a little -1 exponent, and sometimes you'll see the word arc sine. They all mean the same thing. Some people prefer to use arc sine instead of having that sine with a little -1 exponent, just because it's a little cleaner. All right, so when you are evaluating inverse trig functions, you want to be asking yourself this right here. So highlight this, put a circle around it, do something. So we're saying that inverse sine of x, or arc sine of x, means we are looking for the angle between -π/2 and +π/2, whose sine is x. So for inverse sine, again, now we're putting a ratio in for x, and we're getting an angle out, opposite of what we had when we were just doing regular trig functions. All right, so looking at a few examples. It says we want the inverse sine or arc sine of 1/2. In your mind, you're saying to yourself, I need an angle whose sine is 1/2. Okay? Now, arc sine is defined in quadrants 1 and 4. So somewhere in quadrant 1 or 4, we want to find an angle whose sine is 1/2. Well, sine is positive in quadrant 1. So we need to be in quadrant 1. Using all of the information from your unit circle, where do we have a sine of 1/2? And that would be at our π/6 angle. All right, coordinates are √3/2, 1/2. So the sine is 1/2 for the angle π/6. All right, so that's my answer. The second one says we want the inverse sine of -√3/2. So inverse sine is defined in quadrants 1 and 4 again. It is negative in quadrant 4. So we want to be down there in quadrant 4 with an angle whose sine is -√3/2. So here we're looking at our π/3 angles. Coordinates here would be 1/2 -√3/2. So we have an angle whose sine is -√3/2 at this position. But be careful, because we cannot go from here all the way around to there, because arc sine is only defined on the right side in quadrants 1 and 4. So to get there, I'm going to have to simply go in a negative direction down there. So that was a reference angle of π/3. My answer is going to be -π/3. Question C says we want the angle whose sine is π/2. Now, this kind of looks like an angle, but remember, we are taking the inverse sine of a ratio to get an angle as our answer. So let's think of π/2 as a decimal. If you take pi divided by 2, you get 1.57. So we are saying we need the inverse sine of 1.57. But our domain for sine was between -1 and 1. And since this is outside the domain, we're going to just say this does not exist. We cannot do this one. All right. Questions D and E are a little different. We are doing a composition of a trig function with an inverse trig function. So it's saying take the sine of pi over 9 and then tell me the angle whose sine is the same as the sine of pi over 9. Now, these two things should cancel each other out as long as the angle is in a defined quadrant where arcsine is defined. So let's think about pi over 9. That would be in quadrant 1. And inverse sine or arcsine is defined in quadrants 1 and 4. So we are allowed to be there, which means this inverse sine and the sine will cancel each other out, and we simply get pi over 9. For question E, if you think about where 5 pi over 6 is located, that would be over here in quadrant 2. That means we have a reference angle here of 1 pi over 6. We're that much short of being at a full pi. So now it's saying take the inverse sine of the sine of that angle. They should cancel each other out. However, we are not allowed to be in quadrant 2. We have to be in quadrants 1 or 4 for inverse sine. In quadrant 2, our sine value is positive. So we need to bump this to a quadrant where sine is positive, but arcsine is already defined. That means of our choices of 1 or 4, we need to be in quadrant 1, where sine is positive. So we're going to draw that same reference angle of pi over 6 in quadrant 1. So when these two things cancel each other out, you have to be a little careful. If this angle here is not in our defined quadrants, we have to move it. All right, so my actual answer is just going to be simply pi over 6. We just need this angle here. It will have the same sine value as 5 pi over 6. All right, question 2. It says use a calculator in radian mode. So pause the video if you need to switch your calculator to radian mode. This is one that we do not know by hand. We don't know an angle that has a sine of negative 0.81. It's not one of our known unit circle angles. All right, so we're going to use our calculator. You're going to do second sine of negative 0.81, and you should get negative 0.944. So pause the video, try that on your calculator, make sure you're getting the right thing. So that is telling me that the angle that I'm looking for is negative 0.944 radians, since I have it in radian mode. All right, question B. It says take the inverse sine of the sine. So again, those things should cancel each other out. However, 3.49 pi, if we graph that, that's 3 pi plus an extra 0.49 pi. So here's 1 pi, 2 pi, 3 pi, and an extra almost half pi, 0.49. So this reference angle is 0.49 pi. Inverse sine is not defined in those quadrants. So we need to move this either to quadrant 1 or 4. And since sine is negative here, we need to bump it to a quadrant where sine is also negative. That means quadrant 4. And I need the same reference angle of 0.49 pi. And since I'm in quadrant 4, and I can't go through quadrants 2 and 3 to get there, I have to go in a negative direction. So my angle here is going to be negative 0.49 pi. All right, I have to go in a negative direction. All right, moving on to inverse cosine functions. Let's start with our graph of cosine. We start going from 0 to 2 pi. Increments are in pi over 2s. Our cosine curve starts high, goes to 0, low, back to 0, and then high again. Okay? And again, we could draw multiple periods of this, but this is enough. We are looking for an interval Again, that's convenient. It takes on all y values and it would pass the horizontal line test. So for cosine, we are looking at going from here to here. So my interval is going to be from 0 to pi. That's convenient, 1 to 1, and takes on all y values from -1 to 1. All right, so graphing that again, let's look at some ordered pairs. My first point here is 0, 1. My next dot here would be pi over 2, 0. And my third dot is pi, -1. So to find the inverse, we're going to flip those. So we're going to use the points 1, 0, 0 pi over 2, -1 pi. All right. So our angles now go in our y-axis, and our -1 to 1 is our x-axis. Okay, plotting our points, 1, 0, 0 pi over 2, -1 pi. And our inverse cosine curve looks like this. So on our unit circle, we are thinking quadrants 1 and 2, going from 0 to pi. So we can be in this region here. Quadrants 2, quadrants 1. Cosine is positive here, and cosine is negative there. So once again, our domain, we are going from -1 to 1, and our principal value range for this one goes from 0 to pi. It says the inverse cosine function is the function f of x equals inverse cosine of x with domain from -1 to 1 and principal value range from 0 to pi. This means x represents a cosine ratio and f of x represents a positive angle, either in quadrants 1 or 2. The inverse cosine function can also be written as arc cosine. So the question you are going to ask yourself, again, highlight this, put a box around it. Inverse cosine of x means we want the angle between 0 and pi whose cosine is x. We want the angle whose cosine is x. All right, so a couple examples, again, without a calculator here. These are from our unit circle. We need an angle whose cosine is -√2/2. Well, if you think about your unit circles where you have √2/2's, that's our pi over 4. So think in terms of a reference angle of pi over 4. We want the inverse cosine or arc cosine to be defined. That means we have to be either in quadrant 1 or 2. Cosine is going to be negative in quadrant 2. And we want a 45 or pi over 4 angle here. And to get there, we can either be in quadrants 1 or 2. We can move in those two quadrants. So we're going to go from here all the way to there. And we would give our answer as 3 pi over 4, since that's the full angle to get there. Second question says, we need an angle that has a cosine equal to -1/2. All right, cosine is 1/2 at our pi over 3's. So I need a pi over 3 reference angle. Again, cosine is negative in quadrant 2. Arc cosine is defined in quadrants 1 or 2, but it's negative in quadrant 2. We want a pi over 3 reference angle. So to get there, we're going from here to there. So my answer is going to be 2 pi over 3. All right. Third question says we want the inverse cosine of the cosine of -1.1. Now remember, you take the cosine of an angle. So that -1.1 is representing an angle in radian measure. Thinking about our unit circle, here's 0 if we're going in a negative direction. This is pi over 2 negative. Decimal version for that would be negative 1.57. So they're telling me that I have an angle of negative 1.1. So I've gone down and I'm in this quadrant 4 here. My angle is negative 1.1 radians. Inverse cosine is not defined in quadrant 4. So we need to bump this angle, this reference angle, up into quadrants 1 or 2. In quadrant 4, cosine is positive. So I need to bump this into a quadrant where cosine is also positive, which would be up here in quadrant 1. So I'm going to create an angle up here, same reference angle of 1.1 radians, but that is where inverse cosine would be defined. So these are going to cancel each other out, except I need to adjust the quadrant I'm in to make it defined. So my answer is going to be a positive 1.1 radians. All right, moving on to inverse tangent. If we were to graph our tangent function, remember that's the one that's split between negative pi over 2 and positive pi over 2. Distance of that, the period is 1 pi, increments are pi over 4s. All right, at negative pi over 2 we have an asymptote, as well as at positive pi over 2, and our tangent function starts low and goes high. And it has that nice smooth curve to it. All right, so the interval that we would choose is the one we just drew, from negative pi over 2 to positive pi over 2. It fits all of that criteria of taking on all of our y values, being 1 to 1, passing that horizontal line test, and it's a convenient interval, centered again at the origin. Notice here that we are going to put rounded brackets on that interval, since we can't actually be where those asymptotes are. And if we take the inverse of that, instead of vertical asymptotes, we now have horizontal asymptotes. All right, so this is pi over 2, this is negative pi over 2. Our points, we are doing a sideways twist. The point up there, 0, 0, would still be 0, 0. The point pi over 4, 1. Let's try that again. And our other point, negative pi over 4, negative 1. So if we reverse those x and y's, at negative 1, we are at negative pi over 4. We're at 0, 0, and at positive 1, we're up at pi over 4. So we have this twist, but it's more a horizontal twist instead of a vertical twist. Okay, on our unit circle, we are defined between negative pi over 2 and positive pi over 2. So again, in quadrants 1 and 4, the only difference here is we can't actually be on the axis here. We cannot be at pi over 2 or negative pi over 2 because those are asymptotes. So we strictly need to be in quadrants 1 or 4 without touching the axis. All right, domain here is all real numbers. That's different than the other two. Because if you look at our original range, we went from negative infinity to positive infinity. So when we reverse our x and y's, now our domain goes from negative infinity to infinity. Our principal value range would be from negative pi over 2 to pi over 2, not including the endpoints. All right, so in the box here, it's the same thing that we've been reading about sines and cosines, inverse sines and inverse cosines, only relating to tangent. So the question you're going to ask yourself is, when I'm looking for the inverse tangent of x, I'm looking for an angle between negative pi over 2 and pi over 2, whose tangent is x. All right. So looking at example 3, it says find the exact value of the expression without a calculator. We want the inverse tangent of 1. That means I need an angle whose tangent is equal to 1. Well, remember tangent is sine divided by cosine? And for us to get a 1 for an answer there, that means that those two values have to be the same. So where on the unit circle do we have a sine and cosine that are identical? And that is at our pi over 4s. So we are looking for a reference angle of pi over 4. In quadrant 1, inverse tangent is defined. So we can go ahead and use that as our answer, simply 1 pi over 4. The second one says the inverse tangent of root 3. Again, we are saying we need an angle whose tangent is equal to root 3. Well, to get a tangent of root 3, or like we have in our next example here, root 3 over 3, we are looking at ordered pairs of either 1/2 root 3 over 2 or the other one, root 3 over 2, comma 1/2. Okay? So what we have to decide is which one do we need to give us the right tangent. Tangent, we said, is defined as sine over cosine. So to get a tangent of root 3, I'm going to need to have the root 3 piece be on top, which means the 1/2 part would need to be on the bottom. We need sine over cosine, so our ordered pair is going to have to be 1/2 root 3 over 2 to make that work. Okay? So we are looking for an angle that has a tangent of root 3, meaning an angle that has this coordinates. All right? And that is our pi over 3 angle. So we are in quadrant 1 here. Our angle is pi over 3. All right, last one here. It says arctangent is negative root 3 over 3. We need an angle whose tangent is negative root 3 over 3. Hopefully when you look at that, you can tell that it's been rationalized. If we were to unrationalize it, we are saying we want the arctangent to be negative 1 over root 3. That would be the unrationalized version of that. And so when we think about our ordered pair, that's telling me I need the 1/2 piece on top and the root 3 over 2 part on the bottom. Again, this needs to be my sine and my cosine. So I'm looking at this ordered pair here. Where on my unit circle do I have that ordered pair? And that would be at pi over 6. So my answer here is pi over 6. All right. Let me back up a sec. That reference angle had a positive root 3 over 3. We need to have it be a negative. Sorry about that. We need a negative one. So we're going to have to go where tangent is negative, but arctangent is still defined, which would be quadrant 4. So we're going to need to have a negative pi over 6 angle there. So let's change that. Our answer should be negative pi over 6. Once again, we are looking for arctangent to be defined, which we said happens in 1 and 4. And then we need the tangent to be a negative, which would happen in quadrant 4. All right, the last little piece is just asking you to describe the end behavior for our inverse tangent curve, which is this one. All right, first one, this is just the tangent of x. This is the inverse tangent of x. And they're asking for the end behavior. So as we move further to the left, our limit as x is approaching negative infinity, if we go all the way to the left, our function, tangent inverse of x, is approaching, we're going down here, and we're approaching this negative pi over 2 level. The limit as x goes to positive infinity of our function, so as we go towards the right, our function is moving up and it's approaching that pi over 2 level. So you will have a few questions in your homework where it asks you for the end behavior of a graph. All right, so our day 1 homework assignment is page 385, questions 1 through 21. I'm also going to give you a worksheet to just start. I don't expect it to be done tomorrow, but I'm going to have you start the worksheet that reviews graphing sine and cosine with translations. All right, so do this first, but it should be fairly quick, and then get started on that worksheet.